Hello, everybody. Welcome to today's webinar, Direct Injection Engines and Low Speed Pre-Ignition. I am Amanda Harmoning, and I will be moderating today's event. I am an admin assistant here at AERA, and joining me today from AERA is Rob Monroe.
Hello, everyone. I'll be joining Amanda today, and both Amanda and I are going to be in the background. We're going to look after any questions that you may have throughout the presentation. I look after membership and technical development at AERA, and the next few slides, Amanda is going to show you how to use that questions box, and we encourage you to ask any questions that you may have for Lake, and we'll try and help you out throughout the presentation, as well as we'll save some time at the end to also answer any of those questions for you. So I'll turn it back over to Amanda, and she'll just quickly go through on how to use the toolbar.
All right, there's a couple ways you can listen in today. One is via telephone, and the other is your mic and speakers. Please make sure you select the appropriate radio button. This just allows us to make sure that all lines are muted during the presentation. And if you use the telephone, make sure you enter your audio pin and everything as well. And then a couple other things you need to know. There is a grab tab. This is a little orangish red box with the arrow in it. This allows you to collapse and expand your control panel so that it's out of the way while you're viewing the presentation. And the last item is the questions box, and this can be found at the bottom of that window. And you can go ahead and anytime during the presentation you have a question or a comment, go ahead and put that in there. And as Rob mentioned, he and I will be behind the scenes getting those answered. And if there's time, we'll do a live Q&A with Lake at the end. So thank you all, and at this time, I will hand things back over to Rob.
Great, thanks, Amanda. Just a couple quick announcements before we head over to Lake and let him do his presentation. If any of you are going to be anywhere near Redondo Beach, California on June 9th, AERA and SCAT Crankshafts is going to have a Tech and Skills Conference on that Saturday. And we've got a great technical presentation lined up there for you. Lake will be speaking again on that Saturday. We've got Dick Boyer of World Products, Tom Lieb of SCAT Crankshafts, Ron Sledge of King Engine Bearing, and Scott Saprizio of United Engine M Machine. So not only do we have the technical presentations, lunch will be supplied at this particular conference. There'll be a special guest star there, actually, Jimmy Shine. For those of you that are familiar with Fox Sports or Hot Rod TV, you might have seen Jimmy's shows on there. The biggest thing about these tech and skill conferences is the ability to network. We really encourage that at AERA, to be able to provide events where you can get together with other shop owners, other business people. The vendors are also there, so there's manufacturers at these particular conferences. And it's just a good event to be able to go and learn some new stuff, get rejuvenated, come back on a Monday morning after you've been, and you can always apply what you've learned right first thing into the shop. So that's why we encourage these events. This one's going to be pretty popular, so it's going to fill up really fast. If you go to www.aera.org, you'll see right on our homepage, you'll be able to click the link and register for this particular conference. So again, anybody June 9th on that Saturday, SCAT Enterprises and Redondo Beach is the place to be. So it gets you signed up for that one. Another quick announcement, a newer program to us at AERA is our custom training program. Chuck Lynch is one of our techs here at AERA, and he's got 25 years in the industry, 20 of those in the PER side. So Chuck has played roles as process engineer, including quality auditor. And this particular program is for AERA members, and it's a member benefit to our members. So what we can do is you can have Chuck come to your shop, and Chuck can help you with stuff like product failure analysis, tool optimization. You might even have a new component that's new to you that you don't know how to machine, and maybe you need training in that particular end of it, and Chuck can help you with that. Chuck can also help you with setting up a piece of equipment. You know, maybe you've got a new, like I say, a new component for that particular equipment, and Chuck can help you with that. To get a hold of Chuck, if you got any questions about this program, it's right here on the screen, his email address, or you can go ahead and contact him there, and we'll get you set up with that. And again, that's a new member benefit for those members of AERA. I encourage you to take advantage of that. Shops are super busy right now, so even not having time to train properly, you could bring Chuck in for just that particular item. You could have him train your, and help your technicians out and get those looked after. So right now, we're going to turn it over to Lake. He's got a great presentation to do today, and we're excited on this one. This is some of the topics that we're starting to see on the tech line, some of these new types of failures that we haven't seen before. So Lake is a certified lubrication specialist at Driven Racing Oils, and today he's going to go in depth on the low-speed pre-ignition direct injection engine. So right now, I'm going to turn it over to Lake. And how's it going, Lake? How you doing today?
Doing well, Rob. Thank you. All right, can you hear me good?
Yeah, you're coming in loud and clear for sure.
All right, fantastic. Okay, making sure the audio is working there, and my screen's up, so we're ready to get going, huh?
Looks good.
Okay, all right, here we go. Thank you for everybody for attending today. I really appreciate it. Bear with me a little bit. This is going to be the first time going through this. This is a new presentation. It's called, culmination of, as you'll see, several years of work that's gone into working with a couple of different entities, digging into low-speed pre-ignition. And as that failed piston right there in that screen shows you, it's a pretty severe problem. It's pretty unique, and let's go ahead and just dive right into it, if we will. Again, I'm Lakespeed Junior, member of STLE, and my dad was a NASCAR driver for 20 years, and so I've grown up around racing engines my whole life. I really do have a passion for engines. I love engines, and I love racing, and there's a lot of this stuff that came up with the LSPI that really started to kind of ring some bells and remember some things in the past, and I think there's some connections there we might be able to talk about a little bit later. But the interesting thing that's come up is this whole concept of low-speed pre-ignition, which is, it's a detonation event. It's a little bit more unique than that. Obviously, the extremeness of the failure kind of says, okay, well, it's not just a normal knock event. This is something way more than that. Obviously, you want to have spark initiate ignition. You don't want to have pre-ignition, pre-spark ignition. They call it LSPI, the low-speed pre-ignition, as this basic slide says. It's something that's really unique to direct injection engines, and more so in turbocharged direct injection engines. And we'll talk a little bit about that, why turbocharging, not just because of increased cylinder pressure, but also because of poor cylinder scavenging because of back pressure, is one of the reasons why you're seeing this buildup of low-speed pre-ignition. The interesting thing about low-speed pre-ignition is it's random. It takes a long time for these events to occur. Unlike where if you decide to just put a lot of the timing advance to it or run an engine a little bit leaner, you can sit there and make it knock, on a fairly regular basis. Low-speed pre-ignition is more of this kind of random event. And if you get the conditions right, it can happen. It doesn't mean you have the conditions right. It's going to happen, in a given amount of cycles. In fact, when they do the testing for low-speed pre-ignition, which we'll talk about a little later, which is the sequence 9 test. That test, that's how many events per million engine cycles. So that kind of gives you an idea of how random the event can be. But as you saw in the previous piston image, when it does happen, it can be fatal. So it's a real big problem we have to deal with. So the biggest thing we're really seeing is, and we're kind of talked about it a little bit already, is that there's this definite link between LSPI and direct injection engines, specifically turbocharged direct injection engines, and it's severe. And there's a lot of theories about what actually causes LSPI. But what we do know for a fact, and there's research from several entities that prove it, that the formulation of the motor oil has a direct impact on the tendency for these LSPI events to occur. And that's the real thing that kind of, got the whole oil industry up in alarms, which is why there's a brand new oil spec coming out right away. And GM came out with a new oil spec last year to address the fact that the motor oil formulation has a direct impact on the tendency for these events to occur. And what it looks like from the advanced engine testing and a lot of research, fundamental research, is that the droplets of the oil in the cylinder wall and in the ring package seem to be combining with droplets of fuel. And that combination of the oil and the fuel, this is where things can go bad. We've even done testing where we took fuel and ran it through the octane tester and then began adding oil, different oils with no additives in them, just base oil, to the fuel to start checking the octane level to see what would begin to happen at different levels and treat rates and different types of additives, and have the effect on what happens with the octane, because we were able to really see that there's a link here, and we need to investigate what's causing this LSPI and what in the oil is attributing to that happening. And now, before we get into the chemistry of the oil and what's going on, one of the things that we really had to fundamentally question is, well, why is this occurring in direct injection engines and it's not occurring in port-injected engines or carbureted engines? It's not like we've only run turbochargers on DI engines. It's not like we've only run high compression in DI engines. These are things that have been around for a long time. Why is it unique to that? And I think the thing you have to start with is we have to start thinking about time in degrees of crankshaft rotation. As we all know, it takes 720 degrees of crankshaft rotation to complete all 4 engine cycles in a traditional 4-cycle engine. When you start thinking about that in terms of carburetors and port fuel injection, say traditional small block Chevrolet, your intake valve begins to open before the exhaust stroke is finished, and you've got your carburetor way upstream from the valve, the port injections even upstream from the valve. So if you kind of do the math a little bit, the fuel has essentially at least 360 degrees of crankshaft rotation for the fuel to vaporize. And I want to make a good point here that atomization and vaporization are 2 different things. Atomization is the distribution of fine droplets of fuel in the airstream. You want droplets of fuel in the air, not big drops of fuel laying in the manifold or the intake runners. Vaporization is the change of that liquid droplet into a vapor. As we all know, we don't burn liquid fuel. The fuel must be vaporized for it to burn. And so that's a real key thing to keep in mind here, is it's not just atomization of the fuel. We're talking about vaporization of the fuel. So in a traditional carburetor or port-injected system, we have a lot of time for the fuel to not only atomize, but more importantly, for the fuel to vaporize. And you begin to look at direct injection, and here's a little slide from Porsche from several years ago, 10 years ago, for a matter of fact, that basically shows the amount of time that direct fuel injection has to vaporize the fuel is significantly less than the amount of time in a port fuel injected engine or a carbureted engine has. So our problem is a bit of a time problem. When you have less time for the fuel to vaporize, and especially at low engine speeds, when you have less volatility, you have less temperature, and now is a good time to point out that in the research that's been out there, it's very clear that LSPI tendency is greater at lower engine temperatures than at higher engine temperatures, which kind of goes back to this whole vaporization issue. We talked about the oil and the fuel mixing. Well, if the fuel vaporizes, it's not going to mix with the oil. But if the fuel isn't vaporized and it's still a liquid, now it can mix with the oil. So the lower engine temperatures less time for the fuel to vaporize does lead to more fuel dilution. And in fact, in used oil analysis samples that we've taken from direct injection engines, the fuel dilution of the used oil is typically double what we traditionally see in port injected engines, especially in winter conditions. I've even seen it being higher than double before because of that. So that's the real fundamental thing I want everybody to keep in mind here, is that these DI engines, while they're incredibly efficient and the high pressure injection does a great job at atomization, the fact that when you have low engine temperature and you have low engine speeds, in that low amount of time for the fuel to vaporize, we end up with higher levels of fuel dilution, and that's one of the real contributors to this issue. And that's all been proven out through the work we've done with Oak Ridge National Lab. We've been involved in this program with them for a couple of years now. The Department of Energy put out a large grant to Oak Ridge National Lab and the Transportation Research Council that's part of ORNL, and they recognize that direct injection technology is a benefit for industry, benefit for fuel economy and for power density, and it's thing that it needs to be mainstream. But there are challenges, and so they've funded this effort to help overcome those challenges. And along the way, Oak Ridge came to us and said, well, hey, we need some help with kind of dissecting the oil so we can do the testing, so we can really know, okay, what part of the oil is the problem, because everything is pointing to the oil formulation being a key contributor to this issue. So that's how we got involved with Oak Ridge, and we started off, working with them with a traditional type setup for them, which is basically take an engine, isolate it down, so we can kind of focus on the fundamentals, really looking at what's going on, which they take, if you kind of follow the slide there, as opposed to letting the engine kind of run on its own, what they want to do is externally control boost, control all the variables, so the engine's not running in just on its own. You're controlling the inlet temperatures, back pressure, coolant temperature, oil temperature. You control all those variables so we can make the engine operate in various conditions in order to study what happens with the engine in those conditions. And then the next thing we wanted to do was kind of prove out the theory, because they had a theory that was you had oil droplets coming out of the ring lands, and these oil droplets were then mixing with the fuel, and there was some kind of reaction. We weren't sure, is it a heat reaction? Is it a chemical reaction that's taking place that's causing this change? But there's this definite theory of, the droplets released, and there's a lot of validity to this theory, that we know that there's been cases where changing the piston design, changing the ring package can greatly reduce, in fact, sometimes even eliminate LSPI. But typically when you're doing those kind of changes, you're also hurting fuel economy because you're increasing friction and changing the oil control to some degree. So there is a definite theory about how this, transportation of the oil up into the combustion chamber and the mixing of the oil and the fuel in the combustion chamber is certainly an issue. The last line on that slide is really key. They really started to focus on that we suspected that it's the trapped residual, which they mean trapped residual unburnt fuel, basically unburnt, unvaporized fuel, residual exhaust was a contributing factor to this. And when you think about, high back pressure on a downsized engine, the higher the amount of back pressure, the less scavenging efficiency you have with the engine, and that lower efficiency leads to more trapped residual. That's what kind of charges the system. We were able to prove that out on a different engine just by changing the exhaust manifold and improving low speed scavenging. We were able to change the knock tendency of the engine, all other factors held constant. So there's definitely something to this. And we we don't have all the answers by this point, but we are certainly starting to be able to validate some of these initial theories, that came about several years ago, and the testing says, okay, yep, this is what's going on. It is the oil and the fuel mixing, and it is dependent upon the trapped gas. And there's a big part there, because when the oil and the fuel mix, bad things can happen. You really, you want the fuel to be the fuel and the oil to be the oil. And we see here is, combining 3 different oils with a given amount of fuel. And you can see that, the one on the very far left, you can see separate droplets of fuel within the oil, but still on bulk, there's a mixing, a homogenization, if you will, of the oil and the fuel, while there's still some fuel held separate. The image in the middle is very milky white, where you have a hard emulsion, where the fuel and the oil are completely emulsified together. And then the far right, where you have a complete separation between the oil and the fuel, where the fuel and the oil don't want to mix. And obviously the far right scenario, that allows the fuel to evaporate due to piston temperature, engine temperature, and make its way out of the oil and make its way out of the engine, so you don't have that mixing. And, in theory, the one in the middle would be the very worst for low speed pre-ignition, because you're trapping those things and you're keeping the oil and the fuel mixed together, and that mixture is going to have a lower octane value, and that could be a big problem. So we were going to try to understand that, because those are just 3 commercial oils, right? So what we started off to do was, working with Oak Ridge, take the same base stock, vary the additive package, and make various combinations of oils, where you had production lubes, we're going to vary the amount of calcium, we're going to vary the amount of anti-wear, which is VDP, in it, we're going to vary the amount of antioxidant in the oil, we're going to vary the amount of detergents in the oil, and we're going to vary the amount of sodium detergent in the oil. It get really complex, because a lot of the research was pointing towards the detergent package, which helps keep things clean, but also detergents, dispersants help suspend contaminants in the oil. And suspending contaminants, the detergents aren't smart detergents. They don't say, oh, that's contaminant, oh, and that's fuel, we'll suspend the contaminant but not the fuel. The detergents tend to suspend the fuel as well. So if we go back to the previous slide, the oil that had the hard separation between the oil and the fuel also happened to have the lowest detergent concentration as well. And that's not surprising based on how detergents function chemically was. So anyway, this is what we set out to do, was to test these things to find out what effect the different chemistry was having on low-speed pre-ignition. And along the way, we decided, Oak Ridge is doing their work, and they're doing it in their engine, and, running it, in a controlled environment where the engine's not allowed to kind of do what it wants to do. We're controlling every aspect and forcing things. We decided we would go buy our own LT1 engine and work with the guys at EFI University, and utilizing the NOx sensor in it, basically run an engine on a normal condition, where the engine's allowed to run at its own speed, or has its own speed, but the temperatures kind of go where they go, and see what happens with the same lubes, same kind of things in that scenario. And what we found was that validated the work before, where we knew that it seemed like the calcium, the sodium, those things are bad actors, and then the ZDP and the moly are good actors. We looked at 3 different base formulations, where you see oil A up here is a mixture of calcium and sodium detergents, and running that engine and that oil in that engine test series, it produced 5 knock events during the testing, where you took the same oil, or same base oil, took the sodium out, increased the calcium, added some molybdenum, which acts as a suppressant, still had 5 knock events. Brought the calcium level down, not quite in half, and kept the moly in there, and all of a sudden, no knock event. So all the literature really pointed in our testing, both at EFIU and through Oak Ridge, all pointed to this calcium, sodium, the detergent package being the real culprit in the situation. And again, our testing data kind of validated that out. The interesting thing is, while all this is going on, we got a call from the Sunoco distributor over in Europe. Sunoco had been selected to provide a control fuel for the Mini Challenge series in the United Kingdom. So they were running all of these minis all on the same control fuel. And right off the bat, they were having some engine problems. Really not on the racetrack, but they were actually having engines fail coming off pit lane. And they blamed the fuel. They started doing some looking, and pretty much they found out, well, all these engines are all turbocharged DI engines. And the problem they were having, even though they were running a race fuel, they were having LSPI events coming off pit lane. When we started looking, well, the oil they were running was a European spec oil that had a super high level of calcium in it, because a lot of the European spec oils are designed both for gasoline and diesel applications. And if you follow oil a lot, you probably know that diesel engine oils typically have a higher detergent package than passenger car oils, very high TBN oils. So this is a very high TBN, high calcium oil. And we said, okay, well, that's a problem. Let's do a real quick swap. Let's get you to a very low calcium oil that has a higher level of moly in it, which is a race oil. Got them the race oil and changed that detergent moly balance, and all the problems went away. So it was kind of a neat real-world test to see, okay, well, here's a problem where they're really having LSPI problems in the real world. Let's make this change chemistry-wise, and can it affect it? And the answer was yes, it certainly affected it. So definitely got a lot of confidence and validation out of that, okay, not only the testing at Oak Ridge is showing in the single-cylinder control engine test that it is the detergent package that's causing the problem. In the LT1 testing at EFIU, yep, the detergent package is causing the problem. And here in the real world, in the mini engine, we're having the same issue. Detergent package is causing the problem. So it's like, no, Doug, guess what, guys? It's the detergent package that's causing the problem. And that's pretty much what the whole industry has said. We've come to find that high levels of calcium above 1,500 ppm, that's where things go bad. You can have calcium in the oil. You just can't have much more than 1,500 parts per million of calcium in the oil, because it has an impact both in the Ford test and the GM test and these other engine tests we've ran. It all backs up to the same thing. The detergent package is the problem. And when you look at the oils that are on the market today, a lot of the oils out there are higher calcium oils, because that's been the detergent of preference. And with going towards longer and longer drain intervals, you typically can achieve that by boosting the antioxidancy package and by boosting the detergent package and the traditional detergent everybody use, calcium. That's one of the big changes that's hitting the industry right now. GM with their Dexos package that just came out or was upgraded back in September of 2017. As you can see on this slide, they cut their calcium package right down to 1,500 ppm, back to where, again, literature, industry testing all kind of points that 1,500 parts per million is the sweet spot for calcium. You go below that, you don't really get any benefit by cutting it, but you lose detergency. So 1,500 parts per million is the right spot to be for your calcium, and that's has been proven out with several different oils. They've been tested and developed specifically for direct injection engines, and you like to have some moly. The oils that are working good on that chart for DI engines have 1,500 parts per million detergent and have some moly in them, and the ones that don't work very well in DI engines don't have those things. And that's where we get to the point where, again, additives really matter. We started off this process, putting base oil in engine oil and mixing it with motor or with fuel and running octane tests, and we found out, the base oil has some impact. What really matters are the additives, and that, calcium and sodium additives increase the tendency for LSPI to occur. The magnesium detergent is neutral. It does not have an effect kind of either way. And then higher levels of ZDP and molybdenum actually decrease the tendency of LSPI. So they act as a suppressant. So those are the key things to kind of take away from the research and the learning that's occurred over the last few years when it comes to the chemistry of oil and how that impacts these direct injection engines. The industry has responded effective this month, here May 2018. The new oil spec is this API SN Plus, which the updated donut is what you see right there on the screen. If it has that SN Plus in that lower right-hand quadrant of it, then that's the updated formula, which would be completely reformulated. The detergent package has to change from the previous SN. So just because it says SN doesn't mean that it's a lower detergent package. It has to be SN Plus for it to have that lower detergent package capable of meeting the requirements for DI engines to pass. That's called the API Sequence 9 low-speed pre-ignition test. The GM Dexos Gen 2, and you'll see that if it has that Gen 2 under the OS and Dexos, then that is also a updated oil that has a reduced detergent package or modified detergent package to pass GM's proprietary LSPI test as well. And if the oil's got both of those, then you're really good. You're covered on the LSPI side. And that's the key thing to keep in mind, is that when you're looking for engine oils for direct injection engines, the worst thing to do is to go put in some diesel oil that has a very high detergent package. I don't care what it's done in other engines in the past. DI engines should not be running diesel oils. They need to be running oils designed for them, and they need to be running oils that meet this kind of spec or have something on them that says, hey, this was made for a DI engine and it's designed for that application. Kind of going forward, one of the kind of neat things we started playing with is back to what we talked about earlier, the atomization of the fuel versus vaporization of the fuel. The chart there on the screen is your fuel distillation curve. That is the percent of the fuel evaporated versus temperature. So as you can tell here, so this is the guys at VP helped us out. They got us a couple of different fuels to test. And so this is the distillation curve of VP C10 and VP C20. And you can tell that both of these engine oils, both of these fuels have, Iran versus MON, right around, typical octane. So the C10 is 100 and the C20 is 98. The key thing to look here is, 10% evaporation of the fuel is at 212 degrees for the C10. 10% of the fuel is evaporated at 158 degrees for the C20. If you look at the C20, 50% of the fuel is gone by just around 200 degrees. By 100% of the fuel is gone by around 230 degrees. Whereas you still have half of the C10 left to evaporate at that same temperature. That's the key thing, is that the C20 is going to evaporate much faster than the C10. But the C10 has a higher octane value. Well, when we ran this engine, we ran these two fuels in a DI engine and measured the knock tendency of those two fuels for the same engine temperature and the same ignition timing. At 120 degrees engine temperature, the C10 knocked, where the C20 did not. And that's only due to the fact that the C20 was evaporating completely, and the C10 did not evaporate completely, and the C20 did evaporate completely. And so that really kind of helps us go back to the what we saw before in the mixing of the fuel, and how the whole theory of LSPI is really centering around the mixing of the fuel and the oil, back to if you can evaporate all the fuel, then it can't mix with the oil, then you mitigate the possibility of having an LSPI event and even a knock event. So one nice thing you get here combustion-wise for the guys who are real combustion gurus who might be watching, obviously if the fuel evaporates completely, you get 100% of the benefit of the heat of vaporization cooling effect, whereas if the fuel doesn't evaporate, well, then you don't get the full effect of cooling, and that raises your pre-compression temperature, which is going to end up with a higher compression temperature in the end, and that puts you closer to auto ignition temperature. So there's a lot of things that are going on here. It's not simple science by any means, a lot of variables, but this was a neat thing to kind of see. In fact, we've written an article about some of this testing, and it's going to be in the upcoming issue of Engine Professional Magazine, in fact, so you definitely want to get your copy of Engine Professional Magazine if you're interested in any of this, because there's a little more detail in that article. Going forward, we're not done. Obviously the testing at Oak Ridge, the funding for that program it has moved on, but we still are carrying on with our work at EFIU, and we're doing some other work with Oak Ridge and GM as well that's going to involve direct injection engines, and we're definitely going to look at LSPI because there's some very novel new anti-wear additives that are coming into the market, because as we saw, increasing ZDDP helps reduce the tendency of LSPI to occur. But increasing ZDDP typically puts more ash down the exhaust, and if the engine is consuming oil, then it can actually begin to poison catalyst. And with lower tension ring packages and things, it's not uncommon to have a little more fuel consumption in these modern engines than we used to have. So there's a problem. They're not ready to just go raise ZDP limits up. So are there other additives we can add to the oil that complement the ZDDP that might have that same kind of reducing effect of LSPI? So we want to look at that. Also, we want to see for friction modifiers, to improve fuel efficiency. Are there friction modifiers like moly that also provide? Moly carries sulfur, and that's the downside, is that when you add sulfur, then there's a sulfur limit on these oils, and they want the sulfur level lower. So are there non-sulfur carrying friction modifiers? And the last thing is DI engines create soot, very similar to diesels, that soot is created in DI compression or DI combustion events, and soot can be a wear problem. So how do you deal with the soot? So there's a lot of work to be done still, and we're going to continue on, and hopefully we'll have future webinars and things to talk about that as we find more information and can share that information. So kind of a quick summary of what we covered today. So I wanted to try to leave some time for some questions. Is LSPI is obviously an abnormal combustion event that can cause catastrophic damage. Research is showing that the oil and the fuel mixing together is the problem, and specifically it's the calcium and sodium detergent levels in the oil that basically are the catalyst to this being a problem. Fortunately, the industry has made some big steps in the last few years, and now we have API SN Plus coming to the market. You'll see that rolling out the rest of this year. GM got a little ahead of the game and hopped out last fall with the Dexos 2 specification that is providing some LSPI protection in those formulations. But we're not done. We're moving. This is not the end point. I know even on the API side, they're looking towards a new specification coming out in 2020 called GF6. We're at GF5 today. GF6 these oils will be built from the ground up to provide LSPI protection. Fortunately, there's products. Obviously, Driven makes a product and GM makes a product with the Dexos 2 that are oils that are built from the ground up already. So there's some things that are available before GF6 hits, but all that is to say that the industry recognizes that there's a need for oils that are built from the ground up for these engines to address these problems, and people are taking action, and there are options that are coming to the market in order to address these problems, because unfortunately, the oil is part of the problem. And the problems that people had in the past are probably related to the oil more than they are anything else. So with that, I'll be happy to take any questions.
Thank you, Lake. No, that's really good information. The good news is that with these failures is that shops are going to be busy. They're going to stay busy. So there are lots of questions that have come in. First one that I've got is, has this type of failure been seen in fuel-injected type engines such as the LS family in vehicles that are under heavy load and delivery type vehicles such as Workhorse or Freightliner?
The simple answer to that question is no. And not what they would consider an LSPI event. Are there, normal knock detonation events in those kind of engines? Well, yeah. But, the LSPI is very unique to the DI engines, and again goes back to the fuel mixing and a lot of the time the distillation issues. I'm not saying there haven't been issues or situations before that are very similar, but they're not the exact same.
Okay. Has it been seen where it would be specific to particular cylinders?
No, that's not been able to been observed, and part of that's due to the random nature. I said before, they're counting in the sequence 9 test, LSPI events per million engine cycles. I can tell you some quick math. If to run 1 million engine cycles on an engine that's turning about 1,500 RPM, you're talking probably somewhere close to 17 hours. So these are really, really long tests they're running to count, capture a small number of events. So it's pretty random in terms of which cylinder they occur in. Now, obviously, I think that, it's more likely to occur in an outboard cylinder that's cooler because there's a greater tendency for this to occur at low engine temperatures. So when the engine's really cold, it's more so, I would say, probably has a greater tendency to occur in outbound cylinders, but there's not enough. It's so random that it doesn't always end up being, there's always cylinder number 8, or something like that.
Okay. Another question for you, Lake. With the LSPI issue, does it make a difference if it is synthetic or conventional motor oil?
There's some literature that says that certain synthetic oils have greater resistance, lower tendency for LSPI, and there are certain mineral oils that have, conventional oils that have a higher tendency to it. And a lot of that really hinges on the emulsification issue. It's not so much that it's synthetic versus mineral. It really is about how the fuel and the oil mix together. But all the research says it's less an issue of synthetic versus mineral than it is high detergent, high calcium, high sodium versus no sodium, lower calcium. The additive package carries much more weight than the base oil type.
Okay. Another one here for you, Lake. If we were to heat the oil in the sump of DI engines, cold start first miles as an example, would this help to reduce the amount of fuel trapped in the oil?
Yes. In fact, I want to give the credit to Shell on this. I'm trying to remember all the different SAE papers I've read over the years on this. There was an SAE paper that was published that detailed the same engine temperature or inlet air temperature, for example, in this test. When they ran higher oil temperature, the LSPI tendency was massively reduced. Like it was even with a higher calcium oil, they had almost no LSPI events in their testing. But at a lower oil temperature, that same formulation, off the chart. I mean, basically, the engine was being almost destroyed every time they tried to run the test. So oil temperature does make a big difference because I mean, a big part of it's going to be the cold oil is going to cool the fuel, and it helps the fuel not want to evaporate, and that's part of the issue.
All right. Engines that have both DI and PFI, are they less prone to LSPI?
Yes, that's the reason why the manufacturers are doing it. There's been some debate within the API community in a group called ILSAC, which is basically an oil group, but oil group made of engine manufacturers, that the OEMs that have employed the mixture of port fuel injection and direct injection don't see the need to change oil as much as the OEMs that are relying solely on direct injection. When you go to port fuel injection, obviously with different strategies, you could choose to run the engine on port fuel injection at lower engine temperatures. In the zone where you have the LSPI would be at greater risk, you could run the engine on port fuel injection and mitigate that risk. And then when you're out of that risk zone, switch back to DI. Be a pretty easy strategy to employ to be able to do that.
All right.
In fact, I should comment. Oak Ridge, in one of their engines, they actually did just that. They added port fuel injection to the DI engine, and they ran the engine both ways. So they run the same duty cycle, both port fuel injection and direct injection, to prove that if you're only running DI is when you have the problem. That if they complemented it and switched it to just port fuel injection, it didn't happen. Now, they didn't have the funding at the time to go to the next level and create a program that would allow them to switch back and forth dynamically during a test between port fuel injection and direct injection. So we don't really know from the Oak Ridge test if they could have eliminated the LSPI by being able to run both under the same test, just alternating in between. They had to alternate hard, either DI the entire test or port the entire test.
Okay. Did you quantify DI injector deposits at the time LSPI occurred due to mileage?
No. Unfortunately, with the engine at Oak Ridge, it blew up quite often because one of the challenges was we were running Halterman Triple E, which is a control fuel, which is a great reference fuel. So it's a really, really good fuel. So to get a quantity of LSPI events in a reasonable amount of time, the engine was run at fairly aggressive back pressures and boost conditions and inlet air temperatures. In fact, one of the tests pretty early on, they had a runaway event and it, destroyed the engine. We went through $50,000 worth of pressure transducers in about 6 months. So we were not able to do that, mainly because to get the number of events we needed in the amount of time we were looking for, the engine was greatly stressed and there was a lot of collateral damage, so it would have been hard to do that.
Okay.
That's a good idea, though. But that one of the things you saw on one slide, they were checking it early on, but they weren't able to make that correlation.
All right. Are you aware, have any manufacturers done any sort of updated recommendations for older engines?
That I don't know. I know that there are some manufacturers with the newer engines that are already stating they want shorter drain intervals in order to kind of account for these changes in formulations, recognize that the longer you go in the drain interval with the DI engine, the more fuel dilution you can get, the greater the risk becomes, especially in an off-the-shelf formulation. So I think there's been some change in new engines, but I don't know of any OEM going back and saying, hey, we want you to change what you were doing in these engines that were built in 2008.
All right. Another question for you, Lake. Can you tell the difference between LSPI and non-LSPI through failure analysis?
Yeah, I would think you should be able to. When you see LSPI, what you're typically seeing are, incredibly large. I debated whether or not to add some more slides to it that we were showing some cylinder pressure traces so you could see the kind of the magnitude between a normal detonation event and an LSPI event. A lot of the combustion guys like Oak Ridge that have been doing combustion research forever, they call it mega knock, right? It's not just knock, it's mega knock. It blows away what is a traditional, detonation event and you can kind of see that from the piston image on there. You think about a detonation event that might lift a ringland on a high, on a performance engine where picks a little kind of a chunk out of it and it's small on the side versus one that takes the entire half of the side of the piston off. And that's typically what you see when you have an LSPI type failure is the piston damage is quite severe. And it almost always comes, off the side of the piston. That it's, coming out of the corners. In fact, there was one of the SAE papers that was published where they were showing that with LSPI, their in-cylinder footage would show flame propagation coming from the ringland. So it wasn't like, okay, here's a spark plug that's in the center of the cylinder, and we're getting, a spark, ignition event happening in the periphery or toward the edge of the cylinder wall, away from the spark plug. These were literally coming out of the ringland. It was incredible. And a lot of times it was multiple places too. It wasn't like, oh, there's one location on the side. It would come from multiple locations. And so I think that's the key thing to see is by looking at failure analysis. If you see these events and you're seeing damage that's really looks like it's coming from the corners, from the ringland area only, and you're not seeing any other kind of issues on the crown of the piston, that's probably a pretty good indication that it's an LSPI event.
Okay. So would you think horizontally opposed geometry would have a higher tendency, like the Subaru or Porsche, due to fuel on the bottom of the cylinder wall?
Yes. And that's just me saying that off my opinion. Yeah, I don't have any data to support that statement, but I think when you just think about it, I think that horizontally opposed engines probably are at greater risk for this than a V-type engine, just because of physics.
All right. We've got time for a couple more questions here, and then we'll have to wrap it up. And any questions that you have that are coming in, keep them coming in. We'll get those over to Lake for afterwards, and Lake will get back to you. So we'll do what we can to get through the rest of them here. What is the effect of changing the air intake temp, as in turbocharging or intercoolers?
Well, when you having a higher inlet temperature is going to, if you look at the ideal gas law, right, and that's what we're doing as an air pump, if you have a higher inlet temperature, then you're starting closer to the auto ignition temperature of the fuel by itself. So that fundamentally by itself is a bad thing. So you definitely want to have a lower air inlet temperature to try to reduce that. The flip side of that, and I think it's where this question was heading, is that if you're maybe highly aggressive on that intercooling, then you're making the charge potentially so cold, especially at low engine temperature overall, not just low inlet air temperature, low engine coolant temperature, you could make it worse. And all the testing, all the literature does point in that direction, that the problem is worse at low air inlet temperatures, and it's worse at low engine coolant temperatures and low oil temperatures.
All right, so there are still a couple of questions here, and like I say, we do got to kind of wrap things up to kind of stay within our hour time frame. We'll get those over to Lake, and Lake will get back to everybody. Lake, we want to thank you. This is great information. Like I mentioned, this is cutting edge stuff. So it's stuff that shops are starting to see come in the door. I know we're getting calls on it on the tech line as well, and some of the failure analysis stuff that we're looking at. This is really good. So we really appreciate your time, and thank you again.
Well, I appreciate the opportunity, and appreciate everybody for tuning in and being patient with me. Again, this is the first time we've really gone through a presentation like this, so this was definitely not my best effort at putting it together cohesively and making sense of it. So thanks for bearing with my illogical ramblings and stumblings and bumblings through it. But again, you're right. This is something that's very relevant to today, that it's a big issue. It's a huge issue for industry, which is why there's changing taking place, because they're not going to change things if there's no problem. And it's definitely a problem because they're changing things. And I'm happy to pass along information we can to help people go the right direction.
Oh, again, thank you very much. And again, anybody that's got questions, even afterwards, Amanda's going to talk about the survey and about the contacts here. Our 3 emails are there. If you have any more questions that you couldn't think of during the presentation, just shoot us an email to Amanda or myself, and we'll get those over to Lake after the fact too. So for now, I'll turn it back over to Amanda. And again, thank you very much, Lake. Very much appreciated.
Thanks, guys.
All right, everybody, just a couple of things to wrap up here. You will get a follow-up email tomorrow to the recording of today's webinar for you to watch at your convenience, share with staff members. It's yours to use as you would like. Also, when you leave today, you will get a survey that pops up. Please take a moment and fill that out. That just lets us know how we're doing. There's also a place in there to ask any additional questions you may have, and as Rob said, we'll get those over to Lake for you. The last bit of information, as Rob mentioned, our contact information is there. You can also reply to any of the emails you get from GoToWebinar about this webinar, and those will come to me, and we'll pass along any information that needs to go to Lake, and we'll get your questions answered. So thank you again, everybody, for your time. We appreciate it, and I hope you all have a great rest of your day.